In this video, we're starting section 4.1 on divisibility in modular arithmetic. So this section is all about, well, when do integers divide other integers evenly, and talking about remainders. So our goals are to construct proofs involving divisibility, perform calculations using something called modular arithmetic and congruences that'll let us more formally talk about remainders and things that those let us do, recognize when and how to construct proofs using mods, and applying mods to derive divisibility rules. So in this video, let's start talking about divisibility. All right, so I want to start with an example. So 3 divides 18. So what that means is when I do the division, 18 divided by 3, that ends up being an integer because it just equals 6. And that's what it means for 3 to divide 18. That when I do the division, I get an integer. I can rearrange this to isolate the 18. So 18 is equal to 3 and then times the 6. Okay, so now we're ready for the definition, which says if a and b are integers and a is not equal to 0, we can say that a divides b, or equivalently that b is a multiple of a, if there exists a k, which is an integer, such that b will be equal to a times k. So if there's some integer that I can multiply a by to get b, that's what it means for a to divide b, or equivalently for b to be a multiple of a. So my notation for this is we write a, I write this vertical line, which means divides, and then b. All right, so let's do an example where we practice this notation. So I want to answer yes or no to the following questions. Part A says 6 divides negative 18. So to answer this, using my definition, does negative 18 equal 6 times some integer? And yeah, because it's just 6 times the integer negative 3. So the fact that I can do that and that negative 3 is an integer means the answer to A is yes. 6 does divide negative 18 evenly, or negative 18 is a multiple of 6. So in B, what if I flip it? Does negative 18 divide 6? So now the 6 is over here, and is that equal to negative 18 times some integer? Well, the thing that works in the parentheses is negative 1/3, but unfortunately negative 1/3 is not. It's not an integer. So because of that, the answer to B is no. Okay, what about 4 dividing 0? So is 0 equal to 4 times some integer? And the answer is yeah, because it's 4 times 0, and 0 is an integer. So that means 4 does divide 0, yes. Or in other words, 0 is a multiple of 4. Finally, for D and E, I have does 0 divide 4? And does 0 divide 0? One thing I might notice is, wait, division by 0 is weird. And in fact, in the definition, it says A is not allowed to be 0. So that right away could let me say, I could notice that, wait, in both of these, the A is 0. So it should be no. Like the definition is specifically ruling out A to be 0. But why? Like, why is this actually a problem doing, dividing 4 by 0? Because what that would mean is, can I write 4 as 0 times something? But 0 times anything always just equals 0. So 4 is not going to be equal to this. So we tried to figure out what would work here, but nothing is working. Nothing works. And because nothing works, we can't, as a result, we say 4 over 0 is undefined. We tried to find a value for it, but we couldn't because nothing worked. If I do the same thing for 0 over 0, we'd have does 0 equal 0 times something? But this time we have a different problem, which is, well, everything is going to work. Everything now this time in the parentheses works. And what that would mean is if I try to say what 0 over 0 is, well, the answer is it's everything. But the problem then is if I'm trying to find a value for 0 over 0, I can't just specify one value. Because of that, we say it's undefined. We cannot define just one value for it. All right. So let's end this video by looking at a theorem involving divisibility, and we'll do our first divisibility proof. So the theorem says let a, b, and c be integers, and a and b are not going to be 0. Part 1 says if a divides b and a divides c, then a will divide b plus c or b minus c. Part 2 says if a divides b, then a will divide b times c. So b multiplied by an integer. And part 3 says if a divides b and b divides c, well then a divides c. That's the transitive law for division here. So this third one is actually going to be a homework problem to prove. So in this video, we'll do an example where we prove the first one. But for all of these, it's going to be very similar in terms of the structure of the proof. Ordinarily, I'd start off my proof with scratch work and then do the proof. But for the sake of conciseness in this video, let's dive right into the proof. And also just because the proof tends to be a little bit short for this one. So remember, the if part of the statement I get to assume is true. So let us suppose that a divides b and a divides c. And then let's break down what this means using the definitions. So since a divides b, this means there exists a k, which is an integer, such that b is equal to a times k. So this is saying b is a multiple of a. That's the same thing as saying a divides b. And since a divides c, I can say the same type of thing. There exists an integer, j, I can't reuse the same variable, j, which is an integer, such that, well, now c is a multiple of a. So c is going to be a times this integer j. So now we're ready to do our manipulations. I'm trying to show that a is going to divide either b plus c or b minus c. Both of them are roughly the same, so let's just show one of them. So then, if I look at b minus c, well, I know what b is. So b was just ak, so let's plug that in for the b. And I know what c is. C was a times j. So plug it in for the b. Plugging in for b, b is equal to a times k. Plugging in for c, c is equal to a times j. All right, so the b was a times k, and the c was a times j. What is it that I'm hoping to show? I'm hoping to show that a divides b minus c. So what I want to show that, what I need is, I need my b minus c to be a multiple of a. It's got to be a times some integer. But if I look at my b minus c, we're almost at that point. We just got to factor an a out. So if I factor out an a, we'll get a times k minus j. And now I got it. I should just clearly relabel this k minus j. So maybe I'll call it m be k minus j. In doing that, the b minus c that I started with, b minus c equals a times the thing in parentheses, which is m. And I know m is an integer, because this thing is just subtracting two integers, which is an integer. So what we've shown is b minus c is a times an integer. B minus c is a multiple of a. Well, that's exactly what we want. This means that a divides b minus c. And that proves it. So we could see, hopefully, that it wouldn't be all that different if I changed that minus to a plus. It would be so similar to this. So I won't do that one as well, but hopefully you can see how we would tweak this proof to show that it's true for b plus c. All right, so that completes the proof.